my side. Welcome everyone this morning to our part 4 of the NETZSCH webinar series on dynamic mechanical analysis, the standard in post-procurement assurance for composite manufacturing. My name is Tobias Pflock. Some information before we start. Don't worry, you will get access to the slides later on. There will be a recording available on the internet. There's one available already as we speak. As you hear, we do at NETZSCH Analyzing and Testing, we always do our webinars live. So I'm here sitting or standing right now in Germany in front of the screen giving these talks because we just think this is a good idea to get into direct interaction with us. And there is some interaction. You will be able to just use the chat function on the right. Should normally be on the right, and just type in your questions. We will end this webinar after, I think we'll need about half an hour, 40 minutes for the talk. I'll not go into this too deep, so don't worry, we will not use all morning, but there will be definitely a question and answer session. If you have questions during the talk, please use the chat function as well. Just type in your question, and I won't have time to go into that during the talk, but I will just refer to your questions afterwards. If your questions remain unanswered in this talk as I speak, also do not worry, we will have a recording available, so I will just go through these questions and try to answer them later on. But now let's start with the question, why is dynamic mechanical analysis? What is dynamic mechanical analysis and why it is so important for quality assurance in composite manufacturing? This will be, let's say, an introductory talk. You will get the basic messages about dynamic mechanical analysis. Of course, there's a lot more to it, but this is the scope of the talk as we think. Audioverbindung unterbrochen. What the fuck is going on here?
Hear me because it obviously dropped out. Should be back now. I am not using the Bluetooth connection anymore, but it should still be okay. Okay, so let's start with our slides. I'll be your host today. My name is Tobias Pflock. My background is physics. I used to work on dynamic mechanical analysis for a while at NETZSCH. Let's say for about 5 years. So well, I know the instrument by heart, let's say, and since 2015, I am a business field manager for polymer applications, also dealing with composites, of course. This webinar is part 4 of our series on composites. We've started already earlier. Don't worry, I will come back to I will recap the earlier findings of the other webinars. And it's already the second part that we repeat this series due to high interest in composite testing. So I think there's something in. If you logged in this morning, there's something in for you. And this is not only our own story, but we are cooperating very closely with Fraunhofer IGCV. This is a composite research center in Germany that is headed by Professor Klaus Drexler, well, he is a worldwide renowned scientist on the field of composites, has done a lot of work, and Fraunhofer is working on really applied topics, also, of course, on quality control. And this is why we as NETZSCH cooperate with them to, let's say, stay on track with the latest research. The question that I will answer is, why is DMA, dynamic mechanical analysis, the standard technique for post-process quality assurance? Why not any other technique, and what am I able to learn from this technique? The pickups of the Composite webinar series so far. Well, this is part of a whole story of composite manufacturing, and we as NETZSCH, as suppliers of instruments for quality control and for material testing, just display how we take part in this composite manufacturing workflow. We started with the first part, and that is, at some part you have to you have a material, thermosetting resin, and you want to know how to set up your process and how to predict the cure, which is the #1 question for the dominating step for the to control the quality of a composite part. And we displayed how the DSC can be used to derive the respective data, differential scanning calorimetry, and our software, NETZSCH Kinetics Neo, can help you to do a process setup to know at which temperature I cure for which amount of time, and to predict the cure at the end of the process. The second step, was the composite manufacturing. These are all samples that have been prepared, in this case by resin infusion, at the Fraunhofer Center near Augsburg. As a third step, this is what my colleague Alexander Kalupka has shown you. We as NETZSCH have a sensor that is dielectric analysis that we can use for real-time in-process analysis of the curing. So we have a sensor that traces the curing inside of your process. And as a fourth step, we have to do some quality assurance. So we have to see if our process went right. And the #1 method, there's different methods. There's also a DSC displayed here, but the #1 method to do this for composites is dynamic mechanical analysis, for a very good reason that you will learn in a second. So there's 3 phases: process setup and prediction, where I just mentioned, where we can use the DSC, differential scanning calorimetry. You can use, and we used kinetics modeling, the NETZSCH Kinetics Neo package. Phase 2 is the in situ monitoring, so to see what is actually happening in the process. And we use dielectric analysis for this with a DEA sensor, with a DEA in-mode sensor. And as a third step, the post-process quality assurance, for which we can use the DSC sometimes is used, as well as the DMA, dynamic mechanical analysis, to evaluate the glass transition temperature. So this is what we are going to look at today, and this will be the focus. Before that, I will give you short background information. What is dynamic mechanical analysis for you that are not familiar with it? Let's say it is not really a coffee machine, but at some point I have to know what I'm doing when I operate such a machine. But it can give you very, very valuable information with respect to composite curing. So let's look at a textbook definition. Dynamic mechanical analysis provides information about the viscoelastic properties of a material under small, mostly sinusoidal load as a function of temperature, time, and/or frequency. So you see, this is not so straightforward. We see quite a bit of parameters. So it's depending on temperature and time. That is, of course, what we need to monitor our curing process. And we look at something, and the frequency. Sorry for that. And we're looking at something called viscoelastic properties of our material. This will be what is reflected in our DMA measurement. So what is that viscoelasticity? We can think of a polymer being made up of elastic parts. So they're like spring-like parts you can see here on the right. What happens with the elastic part, you excite a sample, so you display a stress upon your sample. And once you do that, there will be a strain, an instantaneous strain. It just stays like this. If you take away the stress after a while, the strain will just go back. So this is regularly the behavior of a model system like a spring. So you can think of your material containing some spring-like behavior. On the other hand, there's something that is maybe a little more strange. That is viscosity, or let's say more to get a better feeling about it, plasticity. What happens? There's parts of your material that react like a dashpot. You see this unit displayed here with some viscosity, and what happens if you display a stress on it? Then what happens? It doesn't just instantaneously deform, but you will have a strain coming up. And if you take away the stress after a while, the strain will just stay. So this is an irreversible effect. And this kind of is not the opposite of elasticity, but you can see they have some different. They show some different properties of your material. And very, very generally, a viscoelastic polymer can be understood as a combination of elastic springs and viscous dashpots. And of course, this is also true for our composite material, especially as a function of temperature, because all this, both elasticity and viscosity, change with respect to temperature. So this can give us a good measure to look at the mechanical properties as a function of temperature. What we do is this experiment right here. I see there's more people came in right now. Could I just get a short feedback from you if you can still hear me, because we obviously lost the sound again. So could you just use the chat function and type in if you can still hear me? That would help. Yes, it's okay. So thank you for the feedback. So I will just continue. Okay. Welcome to our listeners in Turkey this morning. There's also people from Turkey. Okay, I will just continue with my talk. So this is the experiment that you see here that we do in a DMA. You can see if you look at the dashed line, this is what we start with. We apply a stress on the sample, and we do this in a sinusoidal curve because this is mathematically just very, very easy. And this sample will react. You have here, well, this is the sign that we apply on the sample. It's just a sine curve with a certain frequency. And the sample will deform, displaying a strain. And now there's something happening that can already tell us a lot about the material. The strain will be retarded. So there's this phase shift that we can call delta here, but this is actually nothing else but a time. That leads to a retarded sample response. So it will take a while for the sample to deform after we display the stress upon it. And this deformation, or this retardation, is a material property that we measure. So the viscoelasticity of a polymer leads to a retarded sample response. We will need that in a second, because now we want to calculate the complex modulus. Don't worry if you're not familiar with complex numbers. It's actually just a mathematical trick. So, well, this is just the way they made it, but I will take you through the math on one slide so you know that there's some numbers coming out that actually make sense. We calculate this. The modulus is defined as stress over strain. A miracle occurs. And in the end, we get two numbers. And these numbers will be the results that you get from the DMA. This is E prime and E double prime, which is the real part and the imaginary part. But we are just looking at these two numbers, and the formulas tell us how they are. So this is E prime, this is E double prime, and very often people calculate the ratio of both, E double prime over E prime. And this is nothing else but the tangent. This is the tangent of this sorry. Ich check's. Sorry, Windows kicked me out again. This is the tangent of this of the phase shift. So with that, we have a full set of parameters from which we can learn something about your sample. The interesting thing is, of course, well, I don't care so much about the numbers, but I want to know what these numbers mean for my sample. And this is displayed here. Imagine you take a ball, you drop the ball on the floor, the ball comes back up, and the height to which it comes back up refers, that is easy to see, to the ability to store energy. And this refers to the elastic, reversible, or spring-like response from my sample. And this is why we call this number, E prime, this storage modulus. It is the ability of your material to store energy in these springs. On the other hand, you see the ball that we drop on the floor doesn't come up to the entire height anymore, so we lose some of our energy. Where does that go? This is the dissipated, this refers to the dissipated energy, or the viscous, irreversible, or dashpot-like response. This is why we call this guy the loss modulus E double prime. And so with these two numbers, we already have quite a good picture of what is happening to our material. This is only valid for small deformations, as we do in the DMA, in the linear regime, they say. But I can test both storage modulus, so the spring-like behavior, and loss modulus, the dashpot-like behavior, in one and the same experiment. To point that out more clearly, the storage modulus refers to the elasticity of my sample, so that the structural integrity of my part, and is proportional to the energy that is stored during one period under load. The loss modulus refers to the plasticity of my material. It is a measure for the ability of a material to follow a deformation without breaking. So low loss modulus material would be called brittle. It is proportional to the work that is lost or dissipated during one period under load. And the third parameter that we get is the tan delta. This characterizes the mechanical damping or the internal friction of a viscoelastic system. And this can also be at some point interesting for composites. This is not primarily what we're going to look at today, because we are interested in the temperature dependence of these properties. And this is nothing else but a regular DMA measurement, and shown is the temperature dependence. In the bottom x-axis, you can see the temperature increasing from -100 to 100 degrees. And obviously there's some strange things happening to the parameters. Let's look at the green parameter. This is the storage modulus, and there's a very large drop over 2 to 3 orders of magnitude. And that is, so I say this refers to the stiffness, so we are actually losing the stiffness of our material at this point. The second parameter, the loss modulus, displays a large peak here, displayed in blue, at around the same temperature. And the loss factor just comes shifted a little bit later, that also displays a peak. So what are we looking at here? This is the most prominent transition of the most prominent mechanical transition of a polymer in the regular application range as we use it. And this is nothing else but the glass transition. In this case, an elastomer sample, not a composite sample, of which we'll look in a second, because the glass transition is below room temperature. So let's say glass transition is about from -50 to 0 degrees Celsius. And below that temperature, we are in the glassy state. And you see the glass transition, and it's a transition region. And above that, we're in the rubbery state. So you can already see two things. Glass transition is a transition region. There's no way that the polymer can just switch. And the second thing, of course, this is just the same picture for a composite material, as we will see in a second, but the glass transition is very much shifted to another region. So let's have a look at this. We are using the NETZSCH DMA 242E Artemis to explore that. I will not go into deep into the parameters of this instrument. If you're interested, just come back to me later. There's tons of information that you will find on the website, but I will be concentrating on evaluation of this glass transition temperature. Now, I've been talking about these parameters. What does it have to do with composites? I said the behavior is very, very much the same for composites as well. And for that, we need some relation. If you didn't encounter this, don't worry about the formula up there. You can just look it up in every textbook. But the Di Benedetto relation delivers the relationship between conversion and the glass transition temperature. So I was talking about that at the beginning. We need to know the degree of cure, and in post-process quality control for composites, we have to verify the degree of cure. So with this relation, I can relate the glass transition temperature to the conversion. So let's say to the how much of my thermoset material has already reacted. So if I know the TG, I know the conversion. So let's go back to the composites we tested in the composite series part 1. So this is also where we did our DMA experiments. And let's still look at the kinetic simulation that we did. I hope all of you were with us at that point in time already. And you can see that so this straight line here that you see more to the right, this is the temperature profile, and the lower line is nothing else but the conversion of my material. If we look at the in-process dielectric analysis, if we look at the sensor, you can just see about the same. So this is measured parameter, and you can just see that we actually verified our simulation already. I want to point your attention to one thing, and that is eventually our sample is not fully cured, because we see that in our prediction. So the prediction actually says, hey, it's not fully cured in the end. And our dielectric analysis also tells us that it's still a horizontal line. So our conversion is not fully finished. And keep that in mind for the experiments that we're going to look at in the DMA. So question, is there some post-curing? How can we verify that our sample is fully cured or is not fully cured? And the most common technique still, I bring this up for comparison, to explore the curing behavior can be measured by DSC. This is the first and second heating of one and the same sample that we've been looking at during the post-process with our process sensor with the dielectric analysis. And you see two glass transitions here. I will not go where they come from. You just see them as these steps. However, you see it's not so straightforward to explore the differences. The first heating shows a bump, and the second heating, is this shifted? This is much broader, but well, this is not such a straightforward question to answer. So the residual cure cannot be easily resolved. If you do this with very high fiber volume content materials, this step height decreases more and more. So in order for highly filled composite to analyze this, the DSC, let's say, gets even worse. And this is when the DMA comes into play, dynamic mechanical analysis. This is one and the same sample. And you see, just as I talked about earlier, you see nothing else but the glass transition. We can evaluate 3 glass transition temperatures. For the green curve, that is the storage modulus E prime, you see a drop with an onset at about 95 degrees. For the loss modulus E double prime in red here, you see a peak at the glass transition temperature with a peak temperature of about 103 degrees Celsius. And for the 10 delta shifted to the right a little bit more, you can see another peak displayed here in blue with a top temperature of 106 degrees. So, and this is what the glass transition looks like. The glass transition of a composite material looks like in a DMA measurement. Interestingly enough, this is showing you already we decrease or we lose stiffness of the material by a factor of 5. So this is very, very significant. This is not just a small step like you see in a DSC, but it's a large step. Let's do a second heating. And eventually we see that if we heat over the glass transition, we come back in the first heating, we come back down, and we heat a second time, we see all curves displayed here in as these dotted lines are shifted to the right. So onset is higher, onset of storage modulus is higher, the peak temperature of the loss modulus is higher, and the peak temperature of 10 delta is also higher. And that tells us, so we are shifting the glass transition temperature. That means the resin cure has not been finished after our process. So after the first heating, the cure was not fully done. And my take-home message, and this is the primary take-home message of this talk, the DMA, dynamic mechanical analysis, is the most sensitive technique to detect that. So as the mechanical transition is so large, we can easily detect the glass transition in the DMA. I say if the DMA does not see a glass transition, there is no glass transition. So if we know that, if we think back to the Di Benedetto relation, Di Benedetto says the glass transition temperature is connected with the conversion. We see glass transition is increasing, so is the conversion. So, and that is in very well agreement with what we've been showing in the other webinars as well. If you look at the second webinar we did on kinetics and process prediction, we saw that it's not fully cured. InkPro's dielectric control tells that as well. And post-process quality control using dynamic mechanical analysis very, very sensitively shows you that your part is not fully cured. And while this is just showing why this is so important, this is actually why, especially in the aerospace industry, every part that is built into a plane or helicopter or whatever is verified by dynamic mechanical analysis. There's an Airbus standard. I just Googled this, so you can also find this. This is AITM 1-0003. And that is about the determination of the glass transition temperature by dynamic mechanical analysis. So this is why this kind of test is so significant for composite testing and for the verification of the curing state of a composite material in the aerospace industry. And of course, this is very true for automotive industries and so on as well. There are several standards applied. This is the referring ASTM standard, D4065. There's another one, 5023. Most widely used, I think, especially in the US, is this ASTM D7028. But this is again referring to the same kind of measurement using dynamic mechanical analysis. There's another one that is, well, not so widely used, and as I mentioned, this Airbus AITM 1-0003. So with that, we're through already with the basic message of our webinar. DMA is the method of choice for post-process quality control of carbon fiber reinforced polymer manufacturing. We measure elastic response, which is displayed in the storage modulus, which shows something like the stiffness of the material. We measure the viscous response of our sample, which is the loss modulus. E double prime, that refers to the like behavior, so the energy uptake of my material. And the third parameter is the damping, that is the loss factor, tan delta. From these three parameters, we can learn a lot about our material behavior. If we want to look at the curing state, the DMA directly detects the mechanical glass transition as a drop in storage modulus, a peak in the loss modulus, and a peak in the loss factor. And the DMA is the most sensitive technique to detect the glass transition temperature. And I showed you, if we know about the glass transition temperature, we can deduce the residual cure. So the DMA is the method of choice to verify composite manufacturing processes. And just remind you, as this is a part of our series of webinars, we started along, and you should have the full picture now. We started along with an introductory webinar on material characterization along the carbon fiber reinforced polymer manufacturing chain in the first part. Second part, we were looking at how kinetic simulation can improve the thermostatic curing process, which we did, and we could do predictions of our process. Third, dielectric analysis. Our sensor of the NETZSCH 288 Ionic gives you a tool to have a sensor for real-time composite process analytics. And in the end, in part 4, I showed you that dynamic mechanical analysis is the standard. Why dynamic mechanical analysis is the standard in post-process quality assurance for composite manufacturing. And with that, we're through with this webinar, and actually with our series of webinars. My name is Tobias Flock. This is just my contact data, and I did this together with Dr. Alexander Kalupka. I forgot his PhD, so we put together this information for you. As I said earlier, these talks are all available on the web. You will get access to this afterwards. I mentioned this already. We will send out a survey about this webinar if you liked it or not. I have to apologize for the technical difficulties that occur, but sometimes I still cannot look how Windows is actually working. Just blame Bill Gates. No, I'm really sorry for that. And of course, you will get access to a full recording without these faults. However, now I would still give us, let's say 10 minutes for the time being for a question and answer session, because this is why we as NETZSCH Analyzing and Testing do our webinars live. And I myself, Tobias Flock, am available for another 10 minutes where you can ask some questions about, let's say, composite quality control, as we're talking about, but also, of course, about DMA, dynamic mechanical analysis in general. And I see, as I mentioned this I like really a lot. Your questions are popping up already. So let's go back to the questions here. For the ones who didn't hear that, if you want to get into contact with me, just type your questions in the chat window of the webinar toolbar that you can find on your right. And I will just pick from that list and answer your question. There's a very first question that we received from obviously Korea. Well, good morning to you. It's not quite good morning for you again, because I think the day has already advanced quite a bit. So the question is, how can I access to prior webinar on the web? Most straightforward thing is just Google NETZSCH Composite webinar. We will send around the link after, as your participant, we will send around the link to download this. So there's a landing page where you can have access to all the other talks. And we will also send you just a PDF deck of the slides that I just presented. Thank you, he says. You're welcome. Second question, which DMA type is best for FRP to determine TG? Tensile, bending, shear, or another? That's a very good question because I did not go into this too much. A question that we received from Turkey. Well, I can say still good morning, Turkey. But I can answer this question. All measurements that you've seen here were done in bending. And if I go back and display the kind of sample holder that is used for, let me go back here, the kind of sample holder at the bottom left that is used for testing with respect to AITM, to this ABBA standard. And this is a bending experiment because you will find out that you just need very, very low force. And you can measure along very, very nicely along the whole glass transition. So there's no necessity from a physics point of view to do this in tensile mode or shear mode, which would require a very, very high force. But we only want to see this temperature transition, the glass transition, and that can be very nicely done in a bending experiment. Let's say cantilever bending, as this is done here. 3-point bending would obviously display you very, very similar results, but basically you do this in bending. Next question, I received some thanks from Sweden. Well, you're very, very welcome. Just keep talking about that you like the NETZSCH webinars and keep coming back. Next question, the determination of TG of a composite is more accurate with DMA than with DSC. As he says, because in my old university, we used only DSC for measurement of TG. Let's say DSC has its place. DSC is a very, very straightforward method. So you just place a little bit of your sample in your crucible, you heat up, well, you have sample and reference side, and you see, let's say, the heat flux between sample and reference side, and you can also detect post-process quality control. Why are we using DMA here? Because DMA is just so much more significant, so much more sensitive. If you go back, let's say where I have this, this is also why I brought the comparison here. This is DSC measurements on the slide. And you can see this step function. Well, it's displayed very nicely, but I can tell you this is also because we chose the right sample. In real life, this can get really, really hard. So you have, let's say, fiber volume contents of 80% and higher, which just means there's very few polymer left that you can detect in a DSC. And the DSC needs to see the polymer response, of course. So these steps can get very, very small. Still, there's techniques. People are using temperature modulated DSC. You can look into this a little deeper, but for a very good reason in the industry, if we go to the next slide, DMA is the method of choice. So I can just say that Airbus doesn't mess around with that. If they need to know the degree of cure. And you see, we have a drop by a factor of 5. And that is much, much more significant than DSC. And this gets more significant if fiber volume content changes, but the DMA will always show you this kind of transition, or you would find a peak in epsilon prime, in E prime in the loss modulus somewhere. So this is why the DMA, dynamic mechanical analysis, is more significant. Very good, next question. I will just continue with that. How to decide which value is the exact TG? This is a very good point. Since we have 3 values from storage modulus, loss modulus, and 10 delta. You see here, I evaluated all 3 parameters. So I say the physics does not care that we only want to give one temperature. If we look very closely at the glass transition, it's, as I name it, it's a transition region. So our glass transition is obviously happening in our composite material from, let's take this graph here and look at the x-axis. Let's look at the x-axis. our glass transition goes from 80 to about 120 degrees Celsius. So this is a very broad region already. And now, of course, we have to give, in qualification, in order to qualify this material, we have to give a value. So we have to agree upon which value we take. And clearly said, different standards use different kinds of evaluations. Some standards use the onset temperature in E prime, some use peak temperature in E double prime, and some use the 10 delta peak. You have to, so with your customers and let's say if you're in aerospace, this is very clear. They use the peak in E double prime because it's really easy to find. But you have to look at this really closely. It does not make sense to compare E double prime onset temperatures and or E prime onset temperatures and E double prime peak temperatures for a reason of the physics. But you have to agree upon a value that you use. None of these is actually better. I say the one that comes first, the one at 94 degrees. Well, this shows you when you lose your structural integrity. So in order to know what would be the highest temperature to use this material, this is more correlated to the 94.7 degree and the onset of the E prime. But for the evaluation of the glass transition temperature, it depends on the standard you look at. But please be careful and ask which values you want to compare if you talk to one of your customers or one of your suppliers, and agree upon the same value. Another question is going back to DSC and comparison of DSC and DMA. If it's not possible to get more sensitive measurements for the DSC. And another question is also referred to that sensitivity means dependency on the operator's skill. That is not true. The DMA, by the strength of the signal, if you look at here, if you look on the y-axis, our signal goes from 45,000 megapascal down to about 10,000 megapascal. So this is a very, very large drop, and this just refers to the sensitivity of these kind of measurement. If we go back to, and this is inherent of the technique. If we go back to DSC here, you see the step height. So the step height is clearly displayed. But of course, this still, I know that, and I can tell you that this is a demonstration example. This can get worse. And we only have a delta CP, the value is given here, of about 0.1 joule per gram per Kelvin. With respect to the large drop that we have in a DMA measurement, you will always get a larger drop in a DMA measurement and more significantly be able to see the glass transition temperature in a DMA measurement than in a DSC. This just comes with the with the technique, because, and this is just coming from physics. If our so what our DSC in fact shows here, the DSC shows an increase in the specific heat capacity as you cross the glass transition temperature. So your polymer chains get a higher degree of freedom, and when they can wiggle around, and so you have a higher specific heat capacity. This is basically what the DSC shows. The DMA, so that's kind of, and that determines the step height. If you go to the DMA, this refers to the mobility of the polymer chains, and the mobility and the mechanical property just change. So it's a different value. You look at this with, let's say, a different technique. The DMA tells you about the mechanical properties and the mobility of the polymer chains. And well, if your composite material softens, the polymer chains get so much more mobile. So they are just holding, in our case, the carbon fibers together. And but they just lose, they gain so much more mobility the composite part loses its structural integrity crossing the glass transition temperature, and the effect is physically just higher than the increase in the specific heat capacity that we get from the DSC. So some people say the DSC is a more indirect method to detect the glass transition temperature, and the DMA is really a direct method to display the mechanical properties as they change along the glass transition temperature. Okay, there's one last question. I would still go back to that. Carbon fiber reinforced phenolic composite. Another point, DSC sample preparation is much easier than DMA. I would say the measurement is a little bit easier, but if you take a part if you just saw out a part of your composite part, that is quite straightforward. And of course, this is why Airbus and the aerospace industry has chosen dynamic mechanical analysis for the #1 test to qualify their curing state. Okay, let's go back to phenolic resins. I have doubt in phenolic resin curing time and temperature to be maintained. Will the glass transition temperature using DMA give solution? Yes, very straightforward. What you do is you do a first and your second measurement. We do have a facility in India as well. If you want to reach out for that, we can give you the contact for this later. You do a first heating, you cool down again, you do a second heating. If you see this kind of shift of the glass transition temperature, this is a clear sign that you have post-process cure, or that you have still residual cure in your process. And it does not matter on the time of matrix. I've not been talking about different resins and different fiber orientations and so on, because it's all the same signal that we see. And of course, this is very true for phenolic resin as well. Very last question about kinetics analysis. I would refer back to you to the first webinar, and of course you can get into contact with us so we can settle your questions referring to kinetics analysis as well. There's a little bit more to understand, but this is taking us away from DMA. Still, let's say as there's no more urgent questions, if you have more, of course, just approach us. Well, we try to show you the whole picture of composite manufacturing and quality control related with that along the whole manufacturing chain, using kinetic simulation at the beginning, using the NETZSCH as a process sensor during the process, and using the NETZSCH DMA Artemis, for example, for post-process quality assurance. With that, I thank you again for your attention. Thanks for staying here. Thanks for staying with me during these technical difficulties occurring here. If you want to reach out for us, you just find us on LinkedIn. We have the NETZSCH webinar address where you can generally refer to. We will send out another survey, so nothing will be lost. I thank you once more for being here this morning or during your day already. And stay tuned for some more webinars and have a nice day. Bye-bye.